All right, our last section in chapter 9 is 9.4. It's called Permutations and Combinations. The basic idea in this section is looking at how you can calculate probabilities based on the numbers of ways that certain things can happen. And to start that out, I'd like to introduce you to a symbol that you know and love, the exclamation point, but it doesn't mean I'm excited. It's called a factorial. If you have n factorial, and I'll give you a number here in a minute, but it means that you have the number n times 1 less than that number, and then 2 less than that number, all the way down to 3 times 2 times 1. So for example, if you had, actually, we'll just do the example I have on my next slide. You've got a slide for it anyway, 4 factorial. 4 factorial means that I have 4 times 3 times 2 times 1. That's what that notation means. And then we multiply that out. As long as the numbers are small, we can manage with these values and it works just fine. What is 4 times 3 times 2 times 1? It's 24. Okay. And this works for all whole numbers except for the number 0. Obviously, if I do 0 times something down to 1, it doesn't make sense because 1's bigger than 0 is to begin with, right? By definition, 0 factorial is the number 1. Okay? So we're just going to take that at face value. It's a definition, which means I don't have to justify why it works. It's not provable. We're just using that as a case in point. Okay, 0 factorial is 1. If you've had number theory, and I know some of you have, but not all of you, we encountered the fundamental principle of counting back in chapter 2. So I want to remind you of that from that chapter. It says if event M can occur in little m ways and event N can occur in little n ways, then M followed by N can occur in mn ways. Okay, and we're going to do an example in the next one that's about Pizza Planet. What's Pizza Planet from? Toy Story, that's right. So this is an example of the fundamental principle of counting sort of in big form. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meals would consist of 1 salad, 1 pizza, and 1 dessert? So what this is saying over here is that the number of ways each individual thing can happen can be multiplied together to find the total number of ways that the entire scenario can happen. So if you're looking at this one, I would have the number of ways for my pizza, for my salad, and for my dessert, and we would multiply them together. So how many different salads are there? 3. Pizzas? 15. And desserts? 4. And then what is 3 times 15 times 4? Mm-hmm. 180. So there's 180 different meals. All right, so our title of this section says Permutations and Combinations. So we're going to start with permutations first. There are 2 types of permutations. One is called a permutation of like objects. So before I describe what this actually says, let's just imagine what I'm talking about here. So you have a bag of Skittles. Inside a bag of Skittles, there's reds and purples, and there's greens and yellows and oranges and all the different colors. But pulling out purple Skittle number 1 is no different than pulling out purple Skittle number 5. They taste the same. These are like objects. Does that make sense? But see, it would be different than if I had all of you guys in this room and you were all unlike. Okay, so if I select Kimberlyn, it's going to be very different than if I select Sadie. You're different people, completely unlike. Not like my Skittles. Okay, so this example is Skittles. So if you want to put on something next to this, Skittles, Starburst, whatever candy is your favorite, write it in here. This is an like objects example. So if you have n elements, so like the whole bag of Skittles has 40 of them in or whatever, choose R1 of which are alike, R2 of which are alike. All the objects that are alike are indistinguishable. So all the numerator is the total number of objects in the bag, the total number of Skittles, and the denominator is all the different individual Skittles and how many there are. So maybe there's 5 purple, there's 15 yellow, because really those show up far too often. Can we just get rid of the yellow? And then there's 6 red, and there's 4 green, and there's whatever. You've got these different numbers in the denominator representing each individual Skittle flavor, right? And they're all in factorial form. So I'm going to do my examples with Starburst. In a package of Starburst, there are 4 red, 5 pink, 3 yellow, and 2 orange. And how many different ways can you eat the whole package of Starburst? We're not selecting one item. We're eating the whole package, okay? So how many Skittles do you have total? There are 14, that's right. So if we're using this formula, the 14 is what goes on top. There are 14 Skittles. So 14 factorial. And then the denominator, we're going to select each individual flavor and how many they have. So the first one is listed are red. So there are 4 red, so that's 4 factorial. And then I have 5 pink, so that's 5 factorial. 3 yellow, so 3 factorial, and 2 orange is 2 factorial. Okay, everybody good so far? Okay, that's what the setup looks like. Now, I haven't shown you how we work with factorials yet. You don't just get to start canceling things out. You don't get to cancel out the exclamation. It doesn't work like that. Because 14 factorial means 14 times 13 times 12 times 11 times 10. So if I decided I was going to somehow just cancel my 14 with my 4, I would lose something, right? I'd lose a lot of those digits that I should have there. So I can't cancel them out the way that I would cancel out in fractions normally. But here's what I can do. I can write out that I've got 14 times 13 times 12. And in theory, you could, not in theory, in reality, you could write it down all the way to the very bottom of 1. But you can also stop short. We're going to stop short at 5. And the reason we are is because 5 factorial in the denominator, which is my second factorial there, is the biggest factorial in the denominator. So I could write out 5, 4, 3, 2, 1 on the top, and I can write out 5, 4, 3, 2, 1 on the bottom, but do you recognize that 5, 4, 3, 2, 1 on the top and the bottom would cancel? So 5 factorial on top and 5 factorial on bottom will also cancel. But they have to be perfect matches, not just divisible by each other, like fractions typically are. The rest of my denominator is going to be written out in long form just like I did in the numerator. So I have 4 factorial at the beginning. I'm going to shift this over here. So I have 4, 3, 2, and 1. And then I have 3 factorial. That's 3 and 2 and 1. And then I have 2 factorial, and that's 2 and 1. So this is my 5 factorial is going to cancel. We already talked about that. Everything else can reduce just like with fractions. I don't have any more factorials here, right? So the ones in the denominator are sort of irrelevant, but everything else is canceling very nicely. If you want to pair things together, you can. For example, 4 times 3 is 12. So I can mark the 4 and the 3 in the denominator with the 12 in the numerator. All of this will be able to reduce, and it will come out with a whole number, okay? So if you get a fraction or a decimal when you're done, you have made an error, and it's time to go back and try and figure out where that error was. Everything should reduce perfectly. Here's a 3 and a 2, and that's a 6, so that works nice. And then I have a, let's see, I've got a 2 at the beginning. So this 2 could cancel with a 14, leaving me with a 7. That'd be okay. And then this 2 could cancel with the 8, leaving me with a 4. And if you choose to cancel with something different, it's totally fine. It's not going to hurt anything. The thing that you do want to be careful of is that when you go back, you find all of the values that you didn't cancel, right? Everything that is actually still there. So I have 7 times 13, 11, 10, 9, 4, and 7. And I want to multiply all of those together And your calculator will be your friend to do that. What do we get? Is it 2 million something? Lovely. That's what I have too, Brooke. Thank you. This is the number of ways you can eat 14 Starburst. Distinguishably different ways that you can eat 14 Starburst in this arrangement. It's a lot, right? It's a lot. Okay, so this is permutation of like objects. I want to also show you permutation of unlike objects, and then we will pause on this lesson for today. The thing that you need to recognize, and this is actually true for the permutation one we did before, but it becomes much more important now, is that permutations, or when you're working with something that is a permutation, the order matters, right? If I eat the pink one and then the red one, that is distinguishably different than eating red than pink. Are you with me? Okay? That's a permutation kind of an argument. The order matters. It was somehow different. It may not matter in the sense that it really matters. I mean, you ate the whole thing of Starburst, same number of calories, whatever. But it tasted different. It was a different ordering, okay? So on this permutation of like objects, what you see in the numerator is that same n factorial that we saw in the last problem, right? But the denominator is n minus r. Now, in the case with the Starburst, we ate the whole package, right? But when we're doing permutation of unlike objects, we're not eating the whole package, at least not usually. We're eating just a portion of it. We're selecting just a portion of it. We have 13 people in this room and we only want 4 of us to go on the trip. You know, or whatever the situation is. You're only selecting a portion of something. So the n at the beginning is the number of things you're choosing from, and the r at the end is how many are getting to be chosen. Right? Like your lottery, one winner. They choose one number out of the hat. So here's an example of a raffle. 30 contestants put their names in a hat for a raffle. That makes them unlike objects. They're 30 people. People are not alike. Okay, so that's automatically why we're not in the other scenario. 30 people in the hat for a raffle. First place wins $100. Second place wins $50, and third place wins $25. And you have to distinguish, right? The first person that's drawn out is the one who wins the third place prize, or whatever the order is, but it matters, right? If I'm selected first or I'm selected third, my winnings are different. Are you with me? That's why the order matters here, because the prizes have different values. If the prizes were all $50 prizes, then it wouldn't matter who got selected first, second, or third. They all win the same thing. Okay, and that's what we'll see when we get to combinations in the next part of this lesson. But on this one, it matters. It matters which order they're selected out of the hat. So this is a permutation of unlike objects. I have 30 that I'm selecting from, and I'm selecting 3 winners. So this is a permutation of 30, choose 3. 30 to select from, 3 are being chosen, and the order matters, which makes it a permutation. So in my numerator, I have 30 factorial. And in the denominator, I simply subtract these two. 30 minus 3. If you want to see it written out, write it out. If you just want to jump to writing it down as 27, that's totally cool. Either way you look at it, you eventually get to the point that it's 30 factorial over 27 factorial. Okay? I don't want to write out 30, 29, 20, all the way to 1. That's not a good idea, right? I mean, it's a really long idea. I don't like long. So it's much easier, especially when it comes to a situation like this, to write out only as far as I need to and look for a perfect match. If I get to 27 factorial, there is my perfect match, and I can stop. Again, just like on the other one, this will always result in whole numbers. If you're getting decimals, there's an error somewhere. So the 27 factorials cancel. And your calculator can help you out with 30 times 29 times 28.
24,360.
There are 24,360 different ways that these three winners can be selected. Okay? All right, and we will pick up with combinations and how to combine all of this information next time.